This is lecture number 15 of the course Engineering Mechanics. Let us review what we did in the last class. Suppose I have a general three-dimensional force system comprised of several non-couple and couple forces. Let me represent all the non-couple forces by F's. I'm saying there are n such non-couple forces acting on the rigid body of interest. The RB is M. There are several torques acting as well on the body, and these torques I represent by these double-sided arrows. Okay. So N non-couple forces and T couples of forces acting, T couples acting, and those couples have their torques as C1, C2 all the way to Ct. Now this looks like a complicated force system. I call it complicated because there are numerous forces, non-couples and couple, acting on it. I also call it a three-dimensional force system. The meaning of the three-dimensional force system is that these vectors Fi or Cj, non-couple forces, or the torques, may be oriented in any direction, may be oriented in different directions. There is no restriction on how they are oriented. Different directions. No restriction. No restriction on their orientations. That's what I call as three-dimensional force system. If we use a working coordinate system, say if we use a Cartesian coordinate system, in general all Fi's will be having scalar components in all three directions of the coordinate system, and the same applies for Cj. That's my general three-dimensional force system. Then I showed in the last class that based on the definition of what is called an equivalent force system, this complicated force system can be replaced by an equivalent force system with one single force acting Fr at a point of my choice. Say that point is A. One single force. However, there has to, in general, there will also be a torque acting, and which I call as CRA. R stands for resultant, and this CRA is the torque associated in the force system when the single force Fr has been put at A. This is possible to do it. This is a simpler equivalent force system. Why? Because I have only one single force, one single torque in my force system. I also showed that this choice of point A is arbitrary. One can go ahead and also have a force system in which there is that single force Fr acting at point B, and then there will be an associated torque CRB acting on the body. Of course, CRA and CRB will have some relationship. Those details I discussed last time. This is the overall picture. Then I showed that it is possible to have another force system in which we can put Fr at a point W such that the associated torque will be completely parallel or parallel to Fr itself. Is this force system simpler than the two systems I have drawn here? Yes, I believe they are. It is simpler. It is simpler because in these two force systems, CRA and CRB will has a general orientation. CRA and CRB may have a component along Fr, and it will have also a component along perpendicular to Fr in general. However, in this case, we are confident that the associated torque CRW is indeed parallel to Fr. CRW has no component perpendicular to Fr, and thus we deem this force system to be the simplest equivalent of this force system. This is called the wrench of if this system is 1, this is 2, and this is 3, you can call it wrench of 1 or 2 or 3. However, there is one important point we need to remember, that when you are talking about the wrench of a system, this point W cannot be chosen arbitrarily. Cannot be chosen it needs to be found. There is some restriction on W. W needs to be determined. It follows some restrictions. It is not a free choice. In contrast, when you were considering these two force systems, the choice of A and B was completely arbitrary, completely based on your choice. Alright, this is what we did last time. So wrench is the simplest equivalent of a general three-dimensional force system, right? However, there are some special force systems in which the wrench has CRW parallel also 0. I should call it just CRW. There is no need to put the superscript parallel here. CRW. So the CRW, which is the torque associated with the wrench force system, that will also be 0. It means that the equivalent force system will have just one force acting at a special point W. We want to discuss some examples of such force systems. First special force system for which CRW will turn out to be 0 is what we call as coplanar force system. Coplanar force system. And then there is a type of force system which we will call as a parallel force system. For which we will have CRW as 0. What is a coplanar force system? A coplanar force system is one in which all non-couple forces, which I am denoting by FIs, all FIs are all FI vectors lie in one plane, and if there are torques also in that force system, those torques are oriented perpendicular to that plane, which is having all the FIs. This is a coplanar force system. What is a parallel force system? A parallel force system is one in which all forces are non-couple forces, and those forces are all parallel to each other. That's a parallel force system. Okay. Now let's look at the coplanar force system in a bit more detail. So if I have let's consider this RB, and as I said, in a coplanar force system, all these forces, non-couple forces, are in this plane, and if there are torques, they are their directions. The torque direction is perpendicular to the plane. And my claim is that in this situation, it is possible to have one single force acting at point W, and CRW is 0, and W is a point that needs to be found. It's not an arbitrary choice. Now the fact that CRW, we can find a point W such that CRW will be 0, can be explained by the following observation. The way all forces, non-coupled forces, are oriented, it is absolutely sure, we are absolutely sure that the moment due to all non-coupled forces will be perpendicular to the plane. Why? Because the forces themselves are lying in the plane. The torques Ci, Cj and Ct, they already are perpendicular to the plane, right? So it is clear from this figure that the net moment the net moment arising from all these forces will have to be net moment about any point. Take the net moment due to all these forces about any point A will have to be perpendicular to the plane, right? Whereas the net force due to all the forces, that will be planar. Fr will be in the same plane, it is guaranteed. So Fr will be in this plane, same plane, and Ma will have to be perpendicular to the plane, and that itself gives us this hint that when we go from this force system to this force system, there is no requirement to have a CRW which is parallel to Fr. The net moment is perpendicular to the plane, so CRW, which is an associated torque along Fr or in this plane itself, will have to be 0. Let's take an example. Let's take an example of this coplanar force system, and we will actually find Fr and we will also find W, and we will convince ourselves that indeed there is no need to have any CRW in this case. One single force will give us the simplest resultant or the wrench of the system. Example. Okay. So the RB here, the RB of interest is this. We can think of this as a thin object, and then there are 4 forces acting on it, 4 point forces, 4 non-coupled forces acting at specific points, and all these 4 forces are indeed lying in the plane of the screen. It is a given information. Now we want to find its wrench. And in this wrench, I am expecting CRW to be 0. Expecting. Let's see if I can indeed find that solution or not. My claim is that Let's call this point W. Where am I? I am putting XR, putting FR, and let's call this distance from A to B XR. Now, if the right hand force system has to be equivalent, let's call it FS1 and this is FS2, force system 1, force system 2. If these two have to be equivalent, there are two conditions to be imposed. Condition A of equivalence, net force of FS1 equals net force of FS2. What is the net force of FS1? It is 150. Let's take this as I, take this as J. We have 150J minus 600J plus 100J to 50J should be equal to minus FRJ. I have drawn FR from, maybe I should, let me draw FR going oriented like this. Okay, and in that case FR is a scalar, the symbol FR is a scalar, FR times J becomes the vector force. Alright, 150 minus 600 plus 100 minus 250, the answer turns out to be minus 600J. That is FRJ. It implies FRS minus 600 Newton. This is the net force. Now condition B of equivalence requires what? Net moment due to FS1 about a point, that should be net moment of due to FS2 about the same point. Right? Let us choose that point to be A, that point about which moment will be computed. So I am saying MA equals M prime A, where prime means coming from FS2 and this means unprime means coming from FS1. Okay, what is MA? (150) Newton force passing through A will not contribute to any MA. This other force will. 600 times 1.6 will give us a moment along minus k hat. Then the 100 Newton force with its distance, the 100 Newton force will contribute this much moment, positive k direction, and the 250 Newton force will contribute to 4.8. 4.8 in minus k direction. Okay, and this must be the net moment due to all the forces in force system 2. But there is only one force in force system 2, and that force is Fr, and that we are putting at an unknown location xr. So the moment due to Fr will be the way I have drawn Fr. Fr times xr will contribute to plus k along the plus k direction. Okay. Now this equation has only one unknown. Mind you, Fr is already found to be minus 600 newtons, so it is known. Left hand side, everything is known. The only unknown is xr. You can go ahead and find xr, and it turns out to be 1880 by 600 meters. It's 3.13 meters. All the dimensions that I showed on this figure, they were indeed in meters. So we have been able to find xr. So there is no need to have any CRW placed here. There is no need, because as you see, Fr when placed at this distance from A will match the moment due to all forces in force system 1. So this is an example in which only one single force is required, and that makes the simplest equivalent of the shown force system, a coplanar force system. Now in this example there were no torques. There were no torques in this FS1. Even if there are torques, since it is a coplanar force system, those torques will be having direction perpendicular to the plane, and they will have some components along K which will add here, and it is easy to see that even in that case, when there are some torques acting along K, you will still end up finding an appropriate value of xr. Our conclusion will remain unchanged. You will get a new xr where you can put one single force Fr, and that will give you an equivalent force system, a force system which is equivalent to the original coplanar force system. Okay. So this is the first example of a special force system in which CRW turns out to be 0. The other special case I talked about was parallel force system. However, before I give an example of a parallel force system, I would like to talk about what we call as distributed force system. So far in all our lectures, whenever I had forces, I put those forces like this with a single arrow. Single arrow means there is a force of 50 Newton, for example, acting at this point A. Such a force we call as concentrated force or a point force or Sometimes I also call such forces as single isolated forces. Okay. These forces are all acting at specific points. Okay. But in real life, not all forces come as point forces. Some forces come as what we call as distributed force systems. Now this distributed force system means that it is distributed over space. We can actually classify distributed force systems into three categories. The first is a volume distributed force system. Volume distributed force system. We can talk about, or we do come across, an area distributed force system. And we also approximate some scenarios as line distributed force system. Let us look at the details of these force systems. So a volume distributed force system is such that weight of an object is an example. Let me first write an example here. Gravitational force acting on an RB. Gravitational force acting on an RB. This is an example of volume distributed force. We focus on this RB. Let's consider a small chunk of mass which is in the neighborhood of this particle P. Let this small chunk of mass be having volume dV, right, and its mass is dm. Dm is actually related to dV. I can write that as rho times dV, where rho is the local density at that point. Rho is density of RB material at P. Now this rho can be uniform across the RB, or it may be varying. There are several rigid bodies wherein we find that the density changes with location. Now how does gravitational force act on this RB? So if we focus on this particular chunk of mass, indeed we have a force acting on this small chunk of mass, and that force will be rho times dV, which is mass multiplied by g, right? We can actually treat this as a vector by saying that the acceleration due to gravity is indeed a vector. So this arrow is showing a point mass a concentrated force that can be visualized as the force acting on this small chunk of mass. Let me call it dF. Okay. Right. What will be, if we want to know the net force acting on this RB, of course we can net gravitational force can be found as G rho dV, and that integral volume integral over the entire body. This will give us the net gravitational force, right? Now such point forces are acting over the entire volume of the RB. You go to any location and there you visualize a small mass, and you will have these small arrows you can put as representing this volume distributed force. Now volume distributed forces are characterized by a function FV, a vector, such that its units are Newton per meter cube. We characterize this volume distributed force using such a function. Now in this case, if the force is gravitational, Fv will be equal to rho times g vector. Right? Newton per meter cube. We would like to find the equivalent force system arising because of this distributed force system. So if one has to visualize this force, this is the force system that is acting on this RB, the gravitational force system. It's like this actually. It's like this. Every location you go, there is an arrow showing a force, small force acting there. We would like to see what will be the equivalent force system of this, and I anticipate that this can be represented by one single force Fr, with CRW being 0. I will show that in a little while. So an equivalent volume distributed force being replaced by one single point force. If this is possible, then it will become very easy for us to draw the free body diagram of such RBs later on, when we try to relate the applied force system to the motion of the RB. Right? Otherwise, we will have to draw so many arrows and keep track of them. An example of area distributed force system is pressure force. Pressure force. So if I consider an RB which is exposed to ambient atmosphere, we know that ambient atmosphere has pressure, say Pa, which is Newton per meter square. Okay. Now if I go to a small area on the surface of dA on the surface of RB, right? On the surface of RB, I can put an arrow and visualize a point force acting on that area, and that point force will be dF vector equals what? It will be P times E normal times dA, where P is the local pressure. Let the centroid of this area be P. So P is a point on the surface of the RB, and in the neighborhood of P I have taken the small area dA, of course lying on the surface of the RB, and this is the local pressure at P. What is En? En is local inward normal on the surface of RB. Local inward normal. Why do I say inward normal? Because I know pressure will act towards, it will go inside the body. I mean, the direction of the pressure force will be such that the arrow will be pointing towards the body itself. Okay, so this is dF. In that way, if I draw the full free body diagram, at every small area I have to put these small arrows denoting that we are dealing with an area distributed force. Now an area distributed force is characterized by a function lambda, or I can, let's use the same symbol, FA. Again, this is a vector, and in this case FA has units Newton per meter square. Okay, and if the area distributed force is pressure force, FA will be P times En. Now if it is atmospheric pressure, P will be uniform over the entire surface, but we can have situations in which P may be changing from one location on the RB surface to another. In fluid mechanics, we come across this scenario very often, that the pressure acting on the surface of a body changes from one location to another. Okay, in that case the small p will be changing with the location of point of interest or small area of interest. Nonetheless, we will characterize this area distributed force as with this function Fa, which in this case is P times En. Alright, and if we have to get the net force in this case, then that net force will have to be calculated as Fa dA, and this integration has to happen over the body surface. In this case also, one can think of having an equivalent force system such that you don't have to deal with a free body diagram which looks like this with multiple arrows, rather than one single arrow Fr acting at a special point, say W. That would be nice to have. If it is possible, we would like to have this Fr, and then solve the dynamics of the rigid body of interest. Going in the same direction from volume to area, there are some situations in which we come across an approximately line distributed force system. Line distributed force system. Consider this situation. I have a beam. Okay. Now the beam has, if you look at the cross section of the beam, it is very small. This is the side view of it. Now you may be loading this beam with over this small dimension. Let this dimension be B. We can put heap of sand on this B. B is small. Okay, compared to the length. Say this AB has length L. B is small compared to L. And you have placed heap of sand on it. From this side, from this viewpoint, the heap of sand is like this. Okay, this is all sand you have kept. Now this heap of sand that you have kept, it is exerting, and the gravitational force is there, then of course the sand, this mass of sand is exerting a force system on this beam. This is heap of sand. What kind of force system it is exerting? What kind of force system is the sand exerting on my beam AB? It will be a distributed force system. Distributed force system. Now if you go ahead and connect the ends of these arrows, now these arrows, of course, they are their size. The size of an arrow is showing the magnitude of the local force acting here, and the direction is of course showing that the force is acting downwards because it's gravitational in nature, right? In this case, if I focus on this small part, let's focus only on this small part of the RB. Let its length be dl, right? And let this height of this heap of sand be represented as h of x. H x, where x is this distance. Okay. Height of sand heap. Height changes locally. On this small area, there is a force acting dF on the small length of the RB. There is a force acting dF, which I can write as density of sand, right, times volume of sand on top of this surface. How much will that be? That will be dl times B times h of x. This is the volume of sand. dl times bhx times rho of sand. That makes total mass of the sand multiplied by g. I am keeping the vector sign on both sides. This is the force, this is a point force that is acting on this much length, dl length of this RB located at x. Let me put this as x. Alright. If you want to get the net force, of course, net force acting on the RB, you will have to integrate it. And that would be rho sand bhx times dl integrated along the length from x equals 0 to x equals L. This will give you this full force. A line distributed force like what I am showing here is characterized by a function F subscript L, and this will have a unit, this will have units as Newton per meter. And in this particular case, what will FL be? In this case, FL will be rho sand B times height of the heap of sand times G. Okay. This is how we characterize distributed force systems: volume distributed, area distributed, and line distributed force systems. Now I go back to my main topic, which is considering some special force systems in which the wrench has CRW as 0. I've already considered discussed one case, coplanar force system. One example I showed for coplanar force system. This example. Now let's take another example of a coplanar force system where we have the original force system as a distributed force. Original force system is distributed force, and I will consider first a line distributed force system, wrench of a volume. I would consider first length of a line distributed force system. I'll go with the sand heap example that I explained a couple of minutes ago. So let this line distributed force be characterized by this function FL of x. It is known. We are assuming it is known. I want to replace this force system this length is L. Note, I want to replace this force system by one single force Fr acting at special location W. Let's call this length as XR. Will I be able to do this? I should be able to do this because this is indeed, this force system is indeed a coplanar force system. Even though it is a distributed force system, all the forces, all the small forces that would be acting at small segments of AB, they are indeed lying in one single plane. So condition 1, condition A of equivalence, requires me to match the net forces, net force of Fs1 should go to net force of should be equal to the net force of Fs2. Fs2, the net force is of course Fr times minus J. Take it as I direction and we will take this as J direction. K is coming out. What is the net force in Fs1? The net force in Fs1 can be found as Flx dx. What is x and dx? So I'm considering a segment here which is segment of the RB which is at distance x from A, and on this I have this force Flx dx acting on it, right? Mind you, Flx is the characterizing function of this distributed force system with units being Newton per meter. So this must be the force. So this is the force only on this part of the segment. What will be the total force? The total force will be the integral of Flx dx, x going from 0 to x equals L minus j hat direction. This is the force. So the direction of the force is clear on both the sides. So we will drop the unit vectors, and basically we have a scalar equation which gives me this integral times Fr as Fr. Now this integral can be of course calculated without any trouble, but there is an interesting observation here. The observation is this integral Flx dx over x0 over the range x0 to L is actually the area under the loading curve. Area under the Flx curve in the range 0 to L, isn't it? Area under the Flx curve over the x range 0 to L. So that gives us an interesting conclusion that for a line distributed force system, and the force system is in a plane, as I have shown here, the net force can be readily calculated as the area under the loading curve. Area under the loading curve. In this case, the way I have drawn the loading curve, which is an arbitrary shape, it is not easy to quickly conclude what the area would be without doing the integration. I agree, but then there may be some loading curves for which it is very straightforward to find the area under the curve, and in those cases you can actually avoid doing this integration every time, and instead you can use your existing knowledge about the area of the given loading curve and quickly conclude that FR will be the area under the loading curve. So this is the first condition of equivalence that I have established. Now let's talk about the second condition of equivalence.